Okay, so the last thing we will be doing is the performance specifications in frequency domain, let's say. So specifications. If you have a control system, again, a closed loop system like this one, say R minus controller C of S, plant is G of S, and output is Y of S, and you have feedback. Okay, now for this system, we will specs, which are like the maximum overshoot, settling time, rise time, etc. Okay, these are, we have seen them. These are purely in the time domain. You look at the step response of the system. This is time, this is y of t, and find out how your system would respond. And there is also the steady state error. Of course, there is the stability, etc. We can all decide on these. Now, this is one way of doing things, but there is another way of doing it, which that is to specify these things in the frequency domain. Frequency domain specs, let's say, and typically they will be, there are two of these, and they are, one is the bandwidth of the system, which I'll call BW, and then there is the so-called resonant heat. We try to define these quantities for a closed loop system. Now, we will look at the closed loop system, closed loop, which is, as you might remember, is T of S, which is GC over 1 plus GC, or it is L over 1 plus L, where L is GC, as you remember. For the closed loop system, now for the stability, for the Nyquist stability criterion, we were looking at the plot of the Bode plot or the Nyquist plot of the open loop system. Now we will look at the closed loop plot. Bode plot of T of J omega, a typical, let's say, J of omega, T of J omega will be something like this if we plot it. The magnitude plot, this is omega in logarithmic scale, okay? And this is the T of J omega magnitude, okay? Typically, it will be 1 or at 0 dBs. It will start at 1. And then, let me draw it in another color. Typically, it will be something like this. It will go as 1 for a while, make a small peak, and then start going downwards, okay? So, there are certain quantities. This is 0.707, which is minus 3 dBs, okay? Somewhere around here, this is important. Now, this thing makes a very small peak. Usually, it makes a peak. This thing is called resonance, okay? And that peak is called actually the resonant peak. So the difference between here and here is called the MR, which is the and secondly, the point at which your frequency response crosses minus 3 dB point, where the power of this signal or the system goes to its half. That's how it is defined. And this is called the bandwidth frequency. This is called the resonant frequency. And MR is the resonant peak. Okay, so we would like to, according to our design, these parameters change, the things I have defined, especially these ones, the resonant peak and the omega B, the bandwidth frequency, okay? That is, yes, we change our controller parameters, these things change and they affect the system response. Now, by the way, what does this closed loop system frequency response mean? Let's try to understand that. When this thing is equal to 1, it means basically that in this region, whatever this region is, the output is exactly equal to the input, okay? So let's call this region star. In region, let's say star, the output Y follows the input, let's say, without too much error, with no error, let's say, okay? In this region, you are okay. The output exactly follows the input because the transfer function is equal to 1. Actually, this is the ideal case. We would like the transfer function to be equal to 1 for all frequencies if possible, but that's not possible, okay? So eventually your response is going to go down and the output won't be able to follow the input any longer. So, but in the lower frequencies, the magnitude is approximately equal to 1. So, but after a while, your response is going to go down, and it won't be able to follow your input anymore. That's the region in which this thing starts going down. With frequency at which T of j omega drops to 0.707, which is equal to 1 over root 2, by the way. Of its zero frequency level. This is, by the way, is also equal to minus 3 dBs. Okay. Basically, if you have a high bandwidth system, your system is going to be fast. So bandwidth, which we usually abbreviate with BW, is a measure of speed of the closed loop system. So if you have high bandwidth, means fast response, and low bandwidth means slow response. Okay, so if I come to plot it, it will be something like this. If you have the frequency response of a system, let's say this is a low bandwidth system, and this one, the other one, this is a high bandwidth system. This is low bandwidth. Okay, if I plot this is the frequency response as you have seen. If I plot the time response of this step response, which is a time response of this system, it will be like this. For the slow system, it will take some time. This is the slow system, which is low bandwidth, and the fast system will do, oh, sorry, other color. You know, it will settle down. This will be fast. It will settle down much quicker, okay? So it's a measure of speed. Of course, high bandwidth is desirable. We want it, but it makes the system usually less robust and amplifies the system noise. So there is a limit to increasing the bandwidth. You cannot increase your bandwidth arbitrarily. So high, let's say, bandwidth is desirable, let's say, but let's say makes the system, let's say, less stable. This is the time response. So there is always a compromise. You have to compromise, and there are limits to your increasing the bandwidth. This is bandwidth. The second thing we were talking about was this resonant peak, okay? Which is the, as you remember, the maximum value of T of j omega over omega, okay? That is the peak value of your response. In order to get good response, first of all, this peak resonance is usually not avoidable, okay? You try to limit this T of j omega. And it is, let's say, an indication of relative stability and damping in the system. So if you have, if the maximum value of T of j omega, which is something like this, if it goes too much up, that is, if it goes like this much, this is not good. Okay. This basically means that your system is making too much oscillations. Well, let me just try to draw it with some other color. If you look at the time response of such systems, for example, the first one, the yellow one, will be like this, reasonable, but the second one is going to be well, a lot of oscillations. Okay, so we try to limit the maximum value of this thing, this MR value. This is MR. MR, let's say, should be around, let's say, 1.1 to 1.4, or let's say 2 to 3 dBs at most. Okay. You should not have too much of peak resonance in the closed loop control system. Okay. There should be enough damping in the system. By the way, I should say here, it is an indication of relative stability, and too much MR is, I should say, it is an indication of lack of damping. Okay, when there is a lot of damping, the peak resonance is usually small. So we try to make these quantities as small as possible. Well, we try to increase the bandwidth and decrease the maximum resonance, the peak resonance. Now, for a second order system, this is the last thing. For a second order system, let's say T of S is approximated by a second order system, which might or might not be too accurate. Okay. And the damping is, let's say, less than 1. In that case, the resonant frequency will be equal to omega n 1 minus 2 zeta squared, as you might remember. And the maximum peak value at the resonance is 1 over 2 zeta root 1 minus zeta squared. And we note that it is a function of zeta only. It's a function of the damping ratio only. Okay. And the bandwidth, we can find the omega b as follows for second order systems. Omega n in parentheses 2 zeta squared plus 2. This is just derived from 2 power 1 over 2. What you do is you basically say T of j omega magnitude is equal to 0.707 for omega b. And for here, for finding the peak resonance, actually, what we do is take d by d of j omega by d omega equals 0, and then solve for omega and the value at the peak. Okay. These are for second order systems. For other systems, these are not, this is not true, but they are representative. That is, they show a guideline for you. If you can represent your system approximately by a second order system, you can use these things. Okay. Are there any questions here? Let me, if there are no questions, let me just try to give you one example here using, again, MATLAB or Octave. Now, do you see Octave now?
Yes, hocam.
Yes, hocam.
So let's try to define a transfer function. Let's say, I'll just make it up now. G is equal to transfer function of 1 is the numerator. Denominator will be 1. What would that be? Let's say it is s plus 1, 1, 2, 3, 2, 0. So, but this is the transfer function of s plus 1, s times s plus 1, s plus 2. Okay, very simple system with an integrator in it. And I will try to use a controller that is a P controller. So the system we are going to be looking at will be, let me draw it here. There is a K. This is 1 over s times s plus 1, s plus 2. This is y. S plus, okay. So we want to find out the control for this system. First of all, we can just first look at the stability of this system. It will be the d of s, the closed loop transfer function, as you know, is s cubed plus 3s squared plus 2s plus k, I think. So that immediately from root locus, sorry, not root locus, the root criterion, will give you that k should be less than 6 for stability. That's not too hard to find. Let's try something. K is equal to, let's say, 3. Okay. And then okay. So if you look at the step response of this system, it won't be bad. It will be okay, kind of. We will see. But it takes too much time. I don't know why. Okay. Well, as you see, this is neither too good nor too bad. Actually, it takes a lot of time. There is no steady state error. Okay. Probably you need to introduce some sort of a PD control here, derivative action here. This kind of control is not too good. So if we introduce some derivative action, let's say k is equal to the transfer function of something like this. Let's try to do it now. This will probably do better. Yeah, it's obviously much better. So let's try to use this transfer function to find the frequency response of our system. Now let's try to plot the border plot of our. This is the time response, by the way. Let's use the border plot of. And let's define L, which is G times K, K times G. So this is the open loop. L is the open loop transfer function. So we plot the border of L. And we get the following picture. I think if you want to find the phase and gain margins, you can use the command margin. What does it say? It doesn't say anything. It plots it at least here. Okay. The gain margin is, it says is infinite, and the phase margin is 65.5 degrees. So when the gain you see is when the gain is 0 dBs, you go down, and the difference between your real phase and the phase here is like 65 degrees, which is a lot and which is good. But then when you go to minus 180 degrees in your phase, your gain becomes 0, so that the gain margin is infinite. That's also good. It means that your system is not going to get unstable here. So the gain and phase margins are reasonably good, as we see. Okay, then we can look at, for example, the T transfer function. As we said, is the transfer function of L and, sorry, not the transfer function, but rather feedback of Ln1, unity feedback. This is our closure transfer function. If we plot the border plot of T now, we can see the peak resonance and the bandwidth. Now, the bandwidth, it's not very clear from here, but bandwidth is something like somewhere around here, minus 3 dBs corresponds to 1.3 or something like 1.2 or something like that. I don't think I can draw it here. Yeah, I cannot, but And the peak resonance, there is no peak resonance here. There is no peak in our response because there is enough damping. But if we have done it with the, let's say 3 times G, if we had used the P control only, then we would be seeing a peak resonance. You see, there would be a peak resonance, and the bandwidth would be, well, actually, it's kind of the same, but there is a lot of, there is a peak resonance here. And we are just looking, by the way, this is the closed loop transfer function, not the open loop, as we did in the border diagram of the, when we look at the margins, okay? So this is for the P control. The other one was the PD control. And as you see, if you look at the if you remember, this was, oh, well, it just gets mixed up. I have to close this. So this is the step response of the P control, whereas this is the step response of the so-called PD control, which is, as you see, is much better. And it is also seen in the frequency domain performance criteria as well. Okay, so we use, let's say, these quantities called, let's say, bandwidth and resonant peak as specifications, as criteria to design our control systems. Just as we use settling time and so on, we can use bandwidth and resonant peak and that kind of criteria to design our systems. And as you work with these, they become more and more natural to you because bandwidth specifies the range of frequencies at which your output can follow your input. So control engineers, people who work on controls, use these concepts like bandwidth, resonant peak, phase margin, gain margin, etc. Well, you know, quite frequently, and that's a part of their job. It is the language they use when they design such systems. And as I said, I try to introduce them with as little detail as possible because we don't have enough time in this course. If you can take another course on controls, like on classical controls, then you will be taught these concepts in much more detail. So, actually, that's all I'm going to say for this course, for the time being. If you don't have any questions, that will be it. But if you already have any questions, you are welcome to ask them. Is this a question? Intel, we hear voices from you. Yeah. Okay. Well, I guess you don't have anything to say. So let's stop the recording first.